Tonight we have a cubic congruence modulo 49, and one approach here would be to arduously test all the possible remainders when you divide by 49, and those remainders would be, we could check, and again this would be tedious and not to be recommended, but we could check x equals, x is an integer variable, but we could check x equals 0, 1, 2, and again I'm trying to write down all the remainders when you divide any integer by 49, and those remainders would be 49 in number starting at 0. 0 is a possible remainder if the integer is a multiple of 49. 1 is a possible remainder, if you divide the integer by 49 and get that remainder, and so on. So sometimes this is called integer arithmetic. Now this, of course, is doable but tedious. You get into the double digits and trying to cube a number gets challenging. A better approach here, and I like it quite a bit. Notice that any congruence statement can be rewritten as a divisibility statement, or as congruent. Every congruent statement has a corresponding divisibility statement. And so another way of writing this would be to say that 49, and we're assume x is some solution. Okay, well, another way to rewrite this is to write 49 divides x cubed, and we're assuming that x is a solution to this thing. If it is, then this holds. Okay, again, every congruent statement has a corresponding divisibility statement. Okay, let me put that in parentheses. And what I'm doing, I'm just restating this equation that this congruence we're trying to solve with the divide symbology. This means 49 divides x cubed plus x minus 4, or x cubed plus x minus 4 would be a multiple of 49 either way, okay? But notice that this simple claim, okay, any solution to this has to be a solution to this mod 7, right? And that's very simple, right? 7 divides 49, right? And there's a transitivity going on here. In other words, divisibility is called transitive. If A divides B and B divides C, then A divides C. Okay, so the simple reason this is a solution is 7 is also a divisor of 49, and so that means it would be a solution to this original equation. So you see, that gives us a way to go about this with a smaller set of remainders. You see, there's exactly 7 remainders, and notice what I did, folks. Here they are. 0 is a remainder, 1 is a remainder, 2, 3, 4, 5, and 6 are the remainders. That's a lot better than checking 49 values, right? Okay, now, so what we're doing, we're plugging into this kind of ancillary equation here. And so notice that none of this, like for example, this one's not congruent, 26 is not congruent to a 0, all right? Because if you divide, let me put a not there, folks. 26 is not congruent to 0 modulo 7, because when you divide 7 into 26, you get a remainder of 5, right? 3 times 7 is 21 plus 5 is 26. But notice right here, this guy right here, which turns out to be the only solution, is equal to 7 times 18. Okay, that leaves a remainder of 0, and it's just a multiple of 7. So this is congruent to 0. 5, right? 5. So 5 is a solution to this ancillary equation that we're interested in, or congruence, okay? And you can check the others. All these other, this is not congruent to 0. And again, I'm not going to go through all of them, but this is the only one in the list. So 5 would be the only solution to this equation right here. So what that does for us, though, it gives us kind of a springboard, because if 5 is a solution, 5 plus any multiple of 7 is also a solution, okay? And that's simply because 7m is, by appearance, congruent to 0 mod 7, right? M is just some other integer. So 7m is congruent to 0, and again, it's understood to be mod 7, okay? So what I do is take this and substitute it into our original equation. Folks, see here, this is our original object we were trying to solve. And this all works out rather nicely. And the big deal here is that if you cube a binomial, you're going to have two terms that are powers of 49 or multiples of 49, right? So only two of these terms are going to be non-zero mod 49. And again, you can think of the very last term as being 7 cubed m cubed. That's certainly divisible by 49. The term before that would have 7 squared, okay? So that's why there's fewer terms than you might think right here. 5 cubed is 125. And then y'all remember the form. I'll write that out. Remember a plus b quantity cubed? You have the 3's going on in this binomial expansion, right? You get that's equal to a cubed, right? Plus 3a squared b, right? 3a squared b. Y'all, I'm running out of room here, but that's and so on. Then you have another 3 here, folks. And y'all, I'm running out of space here, but that's, you can see where this 575 came from. I left some of this out, folks, but you get the idea. The 3 explains this 125 for the very second term, or the 525 is explained by the fact you have a 3 here, and then when you do it, you'll see it. And I'll trust that you guys can do this. Now, none of this changed right here. Now, the rest of this is just about reducing this thing modulo 49, okay? The rest is reducing modulo 49. So the first thing I did is just sum up the like terms, all right? And then this is the reduction modulo 49. Okay, for example, 532 is 10 times 49 plus 42 is where this 42 comes from, right? But now you see we caught a little bit of a break right here because notice that this is divisible by 42. Let me just write this down. The GCD of 42 and 28 happens to be 7, right? The greatest common divisor, folks, of the numbers 42 and 28 is 7, right? So you see what you could do is you could factor a 7 out of this, and you would get 6m plus 4, but that would also mean that 7 divides this, not 49, but 7 divides this, right? Because this, you could write this down if you want to, but hopefully you see why this follows. It follows from the fact that these two numbers have a greatest common divisor of 7, which can be factored out. This is what's left, but you can also reduce the modulus. And it's the same kind of divisibility trick. 7 divides 49 is essentially why it works, and the 7 has to go somewhere, right? Okay, so in any event, we get to this point right here, and we're looking for a solution to this. And you'll notice quickly, I'll just write it down, m equals 4 is the only solution. Okay, m equals 4. And that's because you get 24 plus 4 is 28, which is a multiple of 7, right? So m equals 4 is the, and you can check, you'd have to check 0 through 6. But y'all, the cool thing about all this is we never had to go through and check all up 0 through 48, right? So we get m is equal to 4. And then, folks, when you put that, let's see, do we have room here? When you substitute that right here, let's see, we have m is equal to 4. And if you plug that in right here, you get 7 times 4. Let me just write it right here, folks. I don't quite have the room here. But you would, I'll just write it. And y'all, I'm substituting 4 right here. And so what you would end up with is 33 cubed, okay? And then right here, let's see, 7, what was it again? 7 times 4 is 28. So this is plus 33. And y'all, again, I'm taking this 4 and placing it right here, right? In this object right here. And 7 times 4 is 28 plus 5 is 33 right here. 7, again, the same thing. And then it turns out, and you guys can verify, this is a solution. It's congruent to 0 mod 49. Okay. Again, the arithmetic is slightly painful, but you almost already know there's nothing wrong with the math that we've done up to here. The only mistakes you could be making was not reducing these coefficients modulo 49. It's about the only type of error that could happen right here. Everything else is pretty much airtight, I think. So anyway, the solution to the equation is x equals 33, and it's the only solution. X equals 33. Okay. All right, y'all. Again, the big idea behind this method is this kind of this basic divisibility result. Okay, and the transitivity of divisibility that allows us just to check this equation with a smaller modulus. All right, there's only one solution to that equation, mod 7, and that would be 5. This computation right here produces that. And then the trick, I guess, if you want to call it that, if 5 is a solution, anything else that's congruent to 5 mod 7 is a solution. And that's what this statement says right here, where m, I didn't write it down, but of course m is another integer. Okay, m is an integer. A proud member of the set Zahlen, the German word Zahlen, Z-A-H-L-E-N. But anyway, that about does it, folks. I'll write it down here also, x equals 33. It's the solution we're seeking. It's the only number. It's a number between 0 and 49, and it's the only one that actually satisfies that congruence. Thanks for watching.